Good. I briefly saw it. As potential fields are that way, you see them and they disappear. Okay, so I was a bit surprised by the title. Yes, potential fields, a role in understanding Antarctic geology, geodynamics, and climate change. Sort of tends to suggest that we can do everything. Unfortunately, that's not the case. But in simple terms, I guess with the radar data, we can look at what lies under the ice sheet. So we can define the bedrock. However, we need to use magnetics and gravity to look under the bed and try and infer what the subglacial geology looks like. And with magnetics and gravity, we can look further down as well into the crust and lithosphere. And you might say, well, why do I care about that? Geology also does have an influence. First of all, it's the reason why the topography is there in the first place, together with, let's say, the glacial processes. But secondly, it determines a series of boundary conditions. For example, the distribution of sedimentary basins, the distribution of crystalline bed, the heterogeneity in geothermal heat flux, but also some of the basins that lie offshore, which then in turn route some of the ocean waters back to the grounding zone and hence determine ice sheet change. I'm trying to keep myself in the job here. Some of the products, I would say that the magnetic community is perhaps one of the best examples of how you can share data. So what you see on the left-hand side is a map of the magnetic anomaly compilation that was made in 2018. This contained a staggering 3.5 million line kilometers of data. So this really shows you that we have got coverage of a fairly significant part of the continent. This provides us with a unique glimpse to try and extrapolate our 1% of knowledge of the geology that we can see along the coast to the other 99%, which is completely covered by the ice sheet. On the right-hand side, you can see another product, which is a product that was made with Professor Jörg Ebbing in Kiel, which is a product where the aeromag data is corrected using the long wavelength from the satellite mag data. And why is this so important? Because we have this patchwork of all these different surveys and compilations, but they actually all sit at slightly different levels. So when we correct the data, let's say we make these compilations, we then often end up with products that are not actually correct at long wavelengths. So this is quite important. Also conforming the aeromag data over Antarctica means that we can compare it better with other continents. So this was part of an effort to, as part of Free the Earth, to contextualize Antarctica better in a global framework. And at the bottom there, you can see some extrapolations of geothermal heat flux. So we know geothermal heat flux much better in other continents that used to be adjacent to Antarctica. So if we can use the magnetic data in some way to tie better the geology of Antarctica to other continents, we also have an indirect proxy to look at geothermal heat flux. Okay, so this is a very complicated slide, so I won't go too much into detail, but I just wanted to tell you that we have new magnetic anomaly data also beyond ADMAP2, and this is a case from Polar Gap, which was an ESA-funded survey at South Pole. And takeaway message is we can use the magnetic data together, for example, with gravity data, and on the bottom you have seismology, to try and get a view that goes from the shallow geology right down into basically the lithosphere. There's an interesting property of rocks. So basically what happens with depth is the temperature, of course, increases and you get to what's called the Curie depth. And so basically you get to depths, say, of 25, 30 kilometers in the crust, typically, and then you lose magnetization. So you can try and use that information to infer in a very coarse manner what geothermal heat flux might look at. And so we're trying to use this property as part of a major ESA project, which is called 4D Antarctica, which tries to tie together observations from satellite of basically ice sheets and subglacial hydrology with also knowledge of the lithosphere from magnetic and gravity data. Geothermal heat flux is one of the least understood parameters affecting the ice sheet. So what you can see there is a summary from a recent white paper from SCAR, and you can see that all these products, although they tell us that we have a colder East Antarctica, surprise, surprise, a cratonic region compared to West Antarctica, which is a region affected by rifting, the devil in the detail really shows you very, very significant differences. On the right corner there, you can see the differences, for example, between a magnetic and a seismological estimate. And you can see there are huge differences in both East Antarctica and West Antarctica. So, for example, rings might offer us a rather nice opportunity to actually collect the data where we have geology. That might actually help in trying to understand what subglacial geothermal heat flux might be, because we can also measure some of the petrophysical properties. We have other data sets that we can look at large scale, so satellite data sets. So, for example, on the right-hand side, you have another product that was done with the University of Kiel, determining the crustal thickness and the lithosphere thickness. These are very important boundary conditions for understanding geothermal heat flux. So very thick lithosphere is generally conducive to lower geothermal heat flux. On the other hand, if you have quite thick crust and it's quite radiogenic, you might even come up to the opposite effect. So you could have high geothermal heat flux with ancient rocks which are highly radiogenic. This is an example of how we can use satellite gravity data to infer crustal thickness. This is a recent piece of work that we did actually with some Italian colleagues, and also infer potential sediment thickness. But this is also a nice example of how non-unique satellite gravity data is. So you can see there in the Wilkes Subglacial Basin, which is one of the largest marine basins in East Antarctica, we find crustal thicknesses of around 30 to 35 kilometers. And then you look at what seismology gives us, and you can see we have those really purplish colors with over 45 kilometers thick crust. So that's an example of how you have, with two different methods, very different results. Again, rings might offer us another opportunity. For example, we could opportunistically try and install more seismometers along the coast, which could be quite interesting to measure both glacial seismic events, but also to try and understand what the crustal thickness is. So this is just an example using magnetic data of determining geothermal heat flux. And being someone who uses magnetic data is very skeptical about this. But how to say, it seems to give a rather interesting result. So we have rather high geothermal heat flux along the coastline in the region of Thwaites. And this is quite significant, because if we independently look at uplift rates measured from GPS data, we come up with remarkably high uplift rates. And these can only be explained if you have a very, very low viscosity upper mantle. And this would actually work pretty well with having a high heat flux, mantle-derived heat flux in this region. This is not to try and defend this technique, but it's an example of where it looks like it's worked. So a lot more is going on at SCAR. There will be a new presentation. The community has collected a staggering amount of new data. I think something like 680,000 line kilometers or more of data. So the MAG community is really, really active. These are some new compilations that I've put together. And so there will be a tool for everyone to use to infer the data, also where we have it close to the grounding zone. I'm not going to show you this. What I am going to show you is just a very quick snapshot of what might be some ideas of how we could, let's say, get together between the geological and geophysical and the glaciological community. So one obvious one, if we do rings, is we can investigate the geology of coastal regions. And as much as this might seem quite obvious, actually very often we don't do that because we go into interior regions to study tectonics or other regions. So actually I think this will help also communicate in the same language, as the previous speaker said, to some of our esteemed geology friends. Second, of course, we can use the gravity data to estimate bathymetry. We can look at studying geological controls on basins. For example, some years ago, I think in 2012, we published a paper with Rob Bingham suggesting that there was a dynamic connection between the ocean offshore in the Bellinghausen Sea and the grounded part of the ice sheet, and that rift basins were actually steering the warm ocean water back to the ice sheet margin. This remains an untested hypothesis, both in the Bellinghausen Sea and pretty much along the whole of the margin of the Antarctic ice sheet. We can look at geological controls on base of shear stresses. This is a very interesting subject, I think. And of course, what we've seen today, we can look at geothermal heat flux and subglacial hydrology. So with that, I'll pass over to René.
Yeah, no,